Hello, everyone. Today we're going to be talking about the impact of socioeconomic predictors on life expectancy. We're Group 1, and this is our Stat 512 final project. My name is Srinivas Venkatesan.
My name is Ayushi Mohanty.
My name is Manas Bomakanti.
My name is Nihar Ashri.
And my name is Dia Prashant.
And yeah, today we're going to be talking about our results and our findings from our analysis. So yeah, we're going to be breaking up our presentation into 7 main components: our introduction, the 5 questions that we analyzed, and the conclusion that kind of goes into our findings and potential improvements. Starting with the introduction, where we're going to talk about the justification and the background of the study that we performed. So the main reason that we chose to analyze this data set was that life expectancy is a metric that has almost doubled in the past century. It was around 32 years in the 1900s, while it is now 71 years. It's important to look into exploratory and observational approaches to see which factors have resulted in this higher life expectancy overall. This growth in life expectancy, however, is simply just not guaranteed. For example, the US life expectancy has dropped by 3 years in the years 2020 to 2022 due to the COVID-19 pandemic, according to the CDC. Therefore, it's important to identify the factors associated with improved life expectancy to guide public policy and to ensure that this growth in life expectancy is sustained into future generations. Finally, we're going to be talking about the variables in our introduction. Some of the variables here are mostly self-explanatory, but the key ones that we wanted to highlight were status, which stands for whether a country is a developed country or a developing country. We also wanted to talk about total expenditure, which is the ratio of government medical health expenses to overall government expenses as represented as a percentage. And finally, life expectancy, which is the main dependent variables that we're going to be analyzing. And the last portion that we'll be talking about is the model building and cleaning procedure that we had to do to ensure that our models had the most amount of data points to work with. We decided to pick 1 year out of the 16 years represented in the WHO dataset, and we wanted to go with the year that had the most amount of complete cases in the data instances, and we found out that 2014 was the year that contained the least amount of missing values. So we'll be analyzing the predictors for the year 2014 for all of our questions. And yeah, the why that we mentioned is life expectancy, and our first question.
So in our first question, we're gonna see if there is a linear relationship between the individual's health decisions, such as alcohol, BMI, and the thinness, along with the life expectancy. So the predictors we're gonna be using are alcohol, BMI, and thinness. So this is the liters of alcohol consumed by people over 15 years old, the average BMI of the entire population of the country, and the prevalence of thinness among people up to 19 years old in percentage. And to compare these variables with each other, we made sure to standardize each predictor. So from here, I kept the model at the first order due to the AV plots given. So we could see that there's a linear impact in each of these plots. And so that's why I just kept it at the first order. And before we start testing our model, we go into the diagnostics. And from the Shapiro test, we found out there's no violation on normality. But from the BP test, we found out there's a violation on the constant error variance, which we'll talk about in the remedies later. And from the VIF scores, since they're all close to 1, there's no violation on the multicollinearity. And we also want to see if there are any outliers or influential points in the data. Based on the box plots, we can find out that there are no outliers for the alcohol and BMI. However, there are potential outliers for life expectancy and thinness. So from here, we plotted the influence plots of the model, and we found out from Cook's distance and student deleted residuals that there are no X outlying cases and Y outlying cases, respectively. However, from the HAT matrix, we found out there are 3 outliers in the data because some values are greater than 2p over n. And to see if there are any influential points on the coefficients, I plotted the DF betas plots. And since the values were between -1 and 1, there are no influential points. And as I mentioned earlier, we had a violation on constant error variance. So I created a WLS model to make the data homoscedastic. And comparing the WLS model with the OLS model, we found out there's a better p-value, and we do not have enough evidence to reject the null hypothesis, making the data homoscedastic. Now we can finally go on to our hypothesis testing. And from our WLS summary, since we have a p-value less than the alpha and an F statistic that's greater than the critical value, we have enough evidence to reject the null hypothesis. This basically means that at least one of our predictors, alcohol, BMI, or thinness, has a linear relationship in predicting life expectancy of an individual. However, from our R squared, we find out that our R squared is 41%, which means that the model cannot quite capture a fit on the data as it might be too simple. So to see how this predictive performance is, I ran k-fold cross-validation with 10 folds, and from here we found out that the RMSE value is 6.637, which indicates that there's bad predictive performance and there's not a linear relationship between alcohol, BMI, and thinness with life expectancy. And after running bootstrapping with the 95% confidence, we find out that alcohol consumption and BMI have a linear impact, whereas thinness does not have a linear impact on life expectancy. And in conclusion, we found out from the last slide that alcohol consumption and BMI are aspects that suggest a linear relationship, but not the thinness among young people. And we also found out from k-fold cross-validation, we need a more complex model that maybe should introduce polynomial regression sometime in the future when we do analysis. And now we'll move on to question 2.
So another question we wanted to explore is if there's a relationship between immunization rates and life expectancy. Hepatitis B, polio, and diphtheria are the columns in the dataset that I used to help answer this question. They all describe the immunization percentages of the diseases of 1-year-olds that were immunized. So we first use the best subsets algorithm to find out how many parameters to use in the model to best predict life expectancy. The model using 4 parameters has a very low press p-value, meaning the predictive accuracy of this model is greater. There are some models with lower press p scores, but the difference is extremely small. Both the SBC and AIC values are lower in the model with 4 parameters, which shows that this model performs well when trying to explain the current data. Despite the increase in the CP value in the 4-parameter model relative to other models, the overall lower scores in other aspects allow us to affirm that the model containing all predictors remains the most optimal choice. Now we know that we want to use all 3 predictors in our model. Added variable plots can be used to measure multicollinearity to confirm the validity of the model. These plots show that using linear terms of all 3 variables are a helpful addition to the regression model. The graph examining hepatitis B's marginal importance does have a line that only slightly slopes, so we can state that the linear term may be a helpful addition, but there's also a slight possibility that the addition of the term may not contain any additional information. A hypothesis test can be used to confirm this, but first, diagnostics need to be run on the model so that the hypothesis test can yield valid conclusions. In order to test the hypotheses to create a better model, and in order to even examine if influential points and outliers have the ability to skew with the coefficients of the predictors that are present, normality of the error terms must be present, and residuals need to have constant variance. This can be checked through the Shapiro and BP test. The Shapiro test p-value is greater than alpha, so we can conclude that the model has normality in the error terms. The BP test p-value is less than alpha, which means that the model does not have constant variance. Outliers and influential points can be found by using the Hat matrix for X outliers, studentized deleted residuals for Y outliers, and Cook's distance to measure influential points. By doing so, we can assess whether specific data points are influencing or biasing our estimates of the coefficients for the predictors in the model. As can be seen, there are many influential points and outliers in the data. WLS can be used to remedy the issue of non-constant variance or unequal error variance in the residuals. WLS was run 3 times, which is the amount of times it took for coefficients of the predictors to stabilize. The BP test can be run again to check if there is non-constant variance. The BP test now has a p-value of 0.837, which is actually greater than alpha. As there are many influential points and outliers in the data, robust regression can be used to dampen the influences of these cases. Even though there is normality in the error terms, robust regression and bootstrapping are done together so that confidence intervals can be estimated and used to make conclusions in the hypothesis test. Because the added variable plots indicated that hepatitis B may not be a good predictor, a hypothesis test can be done to check if it needs to be removed, with the reduced model being the model with 2 predictors. So we would not include hepatitis B. The full model is all 3 predictors. Bootstrapping confirmed that the added variable, that the confidence intervals that contains a 0 is the confidence interval for hepatitis B. That means that there's a 95% confidence. It can be stated that there's no significant linear relationship between hepatitis B and life expectancy. Therefore, hepatitis B can be removed from the model. The model will now contain polio and diphtheria as predictors. This technique was run on the final model, k-fold cross-validation, to assess the performance of the model. As shown in the slide, the method run was run on 10 folds and given an RMSE of 7.4. This leads to the conclusion that predictions made by the model have high variance. The R squared at 31.5% indicates a potential relationship between immunization percentages, specifically polio and diphtheria, and life expectancy. However, further tests are required to validate this relationship. Additionally, it is necessary to conduct more tests to identify factors beyond immunizations that contribute to a more accurate estimation of life expectancy, given that a significant portion of the variability in Y remains unexplained.
Moving to research question 3, we'll now analyze how the status of development in a country affects the life expectancy. The variables we'll be using for this question are two continuous variables, GDP and total expenditure, and status of the country's development is going to be the categorical variable we use. The continuous variables have been standardized to remove the impact of units. We first begin by building a full model with all continuous variables and their interaction effects. Doing the added variable plots on this model shows us that there is there's an overall linear relationship between the predictors. We see some smaller influential points and outliers as the predictors are added to the model. And the conclusion we can draw from the plots is that the predictors do not, no particular predictor needs to be dropped because of their non-zero slopes. We then conduct a hypothesis test to check for the significance of the interaction terms. We begin by building a reduced model without the interaction terms and a full model with the interaction terms. The result of this hypothesis test yields a p-value of 0.000115, which is less than the alpha of 0.05, which tells us that the test is significant and the interaction terms should not be dropped from the full model. Conducting diagnostics on the full model, we first begin by conducting the QQ plot. The QQ plot shows us a pattern which makes us conclude that there is not normality in our residuals. Using the variation inflation factor, we see that the values are close to 1 for all the three predictors. This shows us that there is no multicollinearity between the predictors. Conducting the BP test on the full model gives us a p-value of 0.262. This makes us fail to reject the null hypotheses and conclude that there is constant variance between the residuals. Looking at the outliers and influential points plot and the table, we can see that there are some X outliers based on the hat matrix. And the graph, there are some Y outliers as well as influential points based on the Cook's distance values. After conducting the diagnostics, we conclude that we have non-normality within the residuals, which can be solved using bootstrapping, and the influential points and the outliers can be taken off by conducting robust regression. As our remedial measures, we conduct robust regression. And after conducting robust regression, we observe that there is some improvement in the residual standard error. It goes from 6.5 to 5.878. We then conduct bootstrapping on the robust regression model. And the confidence interval that we get, we check whether the confidence interval contains a 0 or not. And the results are in the table given on this slide. Based on the results, beta 1 can be dropped, beta 2 can be dropped, beta 3 cannot be dropped, beta 4 cannot be dropped, and beta 5 can be dropped. We did say that beta 1 can be dropped and beta 4 cannot be dropped. But since we want to include an interaction effect in our model, we cannot exclude X1 from the model, which yields the interaction effect. Therefore, the final model contains X1, X3, which is the categorical variable, and the interaction between X1 and X3. In other words, this is going to be the impact of GDP on GDP and the status of the country and their interaction effect. on the life expectancy. Finally, conducting cross-validation, we see that the RMSE is 6.62. This means that the predictions made by the model may have higher variability. With an R-square of only 0.44, we can conclude that only 44% of variability in Y can be explained by the predictors. Lastly, we know that GDP and the status of the country have some effect on life expectancy, but other predictors could be added to this model to improve its performance.
The next question that we want to analyze is that does HIV and AIDS, the death rate of HIV and AIDS in children significantly affect a country's life expectancy, given the death rates of infants and children? Let's first look at the predictors. The first predictor, X1, is the number of under 5-year-old deaths per 1,000 people. X2 is infant deaths, so the number of infants that die per 1,000 people. And X3 is HIV/AIDS deaths, the number of deaths caused by AIDS for 4-year-olds per 1,000 people. The first thing that I did for this model was to clean the data. So I used the omit function to remove all the rows that contained an NA value in the columns I was investigating. And I also used the scale function to kind of remove any units from my analysis and standardize the comparisons. The next thing I did was use the best subsets model to kind of determine which of the predictors would create the best model for me to analyze and analyze my marginal impact for X3. I used the metric for, I chose to use the metric SBCP and PRESS as our data was medium sized, which is better for SPPC. And also SPPC tends to choose the true model instead of more complex models, which I was trying to avoid. So according to this metric system, I chose the model that was in the red box, which is including X1 and X3, removing X2. While it's fair to say that the full model has a lower SSEP and R-squared, it does have a higher SPP and PRESS value, making it a worse choice for my particular question. The next thing I did was go over the diagnostics for this model. I started with multicollinearity, where I experienced no issues. You can look at the correlation values, where the two predictors, X1 and X3, have a very small correlation of 0.1. Also, I took the VIF of both predictors to kind of see how inflated their variances were, and the VIFs were close to 1 and also less than 10, which means that there's no multicollinearity issue there. Next, I looked into normality. The data follows a normal distribution according to the Shapiro test, as the p-value is greater than 0.05, as well as the QQ plot looks fairly normal and follows a linear distribution. Finally, I checked for constant variance through doing the Bruch-Pagan test, where the p-value was greater than 0.05, meaning we failed to reject the null hypothesis. The next, I continued moving on with model diagnostics, but this time I looked at outliers and influential points. I set the thresholds for the different outliers so that in the return value of the influence plot returns the different points of interest and their different values. And then based on those values for studentized residuals, hat matrix, and Cook's distance, you can kind of see which points are more of outliers and which points are influential points. On looking at the Cook's distance plot on the right, you can see that 0.52 has the largest circle and is the most blue, meaning that its Cook's distance is the largest. You can also see 0.103 is at the bottom of the graph, which means that it has the highest studentized residual because its Y direction and Y variance is the highest compared to all the other influential points. This is going to be taken care of in my next slide, where I go over model remedies. Specifically, the only main issue I faced was outliers and influential points. So I used robust regression to kind of fix that. You can see here the residual standard error before robust regression was 6.6, and then after it was 5.6, which is a pretty remarkable decrease in standard error, and it means that the model's predictive accuracy is quite higher. Also, I implemented bootstrapping, which caused, as you can see, the standard error to be higher, which is a consequence of bootstrapping, but also the bias for X3, which is the value that the predictor that I care about adding to my model, is quite small, which means that this bootstrap model does have a high predictive accuracy and is a good way of explaining the data. Now for model validation, before I did my hypothesis testing, I wanted to validate the model that I've created so far. So I used 10-fold cross-validation. It gave a high RMSE value of 6.5. That means that my model has high variance and also weaker predictive power, but it also has R-squared value of 0.53, which means that even with the high RMSE value, there's still moderate explanatory power. Given the simple linear model that I'm investigating, obviously there can be higher order models to be used, but this is the best that I can do for this model. Now, in the hypothesis test, the null hypothesis is that beta 2, which is the HIV and AIDS, the predictor is equal to 0, and the alternative hypothesis is that it's not equal to 0. You can see the reduced and full model on the screen. The points of interest here is that in the bootstrapped confidence interval for beta 2, I found that 0 is not in that confidence interval, which means that beta 2 has a significant marginal impact on the model because it's never 0, which means that it's significant. Also, the marginal impact in the summary for the full model shows that the p-value is 9.2e to the negative 15th power, which is less than 0.05, meaning that there is a significant impact. So to conclude, given my hypothesis test and cross-validation, we can conclude that we should add X2, which is the HIV/AIDS death rate in children, to a model that already has X1, overall death rates for children, as it adds a significant marginal impact. This large impact makes a lot of practical sense, given how deadly HIV and AIDS has historically been.
Yeah. Moving on to our fifth and final question, which is going to be talking about how the government's performance and how the quality of a government services affect the life expectancy of the population. Firstly, we're going to be taking a look at the predictors that we're going to be using, which is going to be schooling, GDP, and total expenditure, which can be classified as predictors that are correlated with overall higher government performance. And we're going to be testing to see if there's a significant relationship between these predictors and Y, which is life expectancy. The model is as shown on the screen. And the first step that I did was to remove all the missing rows from the data frame and scale the different predictors to reduce the impact of units. As you can see on the image to your right, there's limited correlation between these predictors, and this is good to improve the predictive power of our model. To address any potential data issues that we might run into, the first thing that I checked was linearity. And as you can see, schooling and GDP tend to have a marginal linear effect on the prediction of Y, but the line for total expenditure does seem to be pretty flat. Performing the best sub function does tend to validate this hypothesis because we see that the function best sub tells us to drop X3 due to a lower press in SBC value for model index 4. If you look on the image to your right, we also see that there are some influential points that are present in this data set, which we need to address through robust regression. But thankfully, there's no multicollinearity issues because the VIF scores are close to 1 and less than 10. More issues that we could run into, we see that our predictors are not normal, which kind of leads us to perform bootstrapping to answer this question. But we do see that we do have constant standard deviation for our predictors, and therefore we do not need to address this in any way, according to the results of the Birch-Pagan test. So as I mentioned in the slides before, the remedies that we'll be performing are robust regression and bootstrapping. As you can see, the MSE before performing robust regression was 4.984, but after performing robust regression, we see that the MSE goes down to about 4.657, which is pretty remarkable. Furthermore, the new estimates for the parameters after bootstrapping tend to have low bias compared to the predictions from before, and also have a low value for standard error, which is good for our predictive power. And finally, we're going to be setting up the hypothesis test. So to answer this question, we're going to first set a hypothesis test to test the linear impact and the significance of our linear model. We see that beta 1, which is index equals 2, does not have 0 in its confidence interval. So therefore, we can conclude that with 95% confidence that there is a significant linear impact from the variable X1 on life expectancy. However, we do fail to reject the second hypothesis test, which basically is a question of whether beta 2 is equal to 0. Since the interval does contain 0, we fail to reject the null hypothesis. X2, which is GDP, does not have a significant linear impact on Y. Lastly, we're going to be taking a look at the cross-validation performance of my model and potential conclusions that we can make. As we can see on the image to your left, we performed tenfold cross-validation and found out that the RMSE value for our model was 5.09, which indicates that the model does have some bias. However, we also noticed that about 70 to 71% of the variance in Y is completely explained by our predictors, which is pretty good, and which is a sign of really high predictive power. And what we can conclude from this hypothesis test and the cross-validation is that schooling has a significant linear impact on life expectancy, but GDP does not. On average, when people spend more years in school, they tend to be more aware of the healthy habits that prolong their life expectancy. Therefore, these results make practical sense in a real world setting as well. And the model that we finally end up coming up with was y is equal to 42.811 plus 2.1627 times schooling. And moving on to our conclusion.
So some key takeaways from our analysis is that alcohol consumption and BMI have a linear relationship with life expectancy, whereas thinness does not. Hepatitis B immunization adds no value to the model with polio and diphtheria. And diphtheria and polio show moderate linear relationship with life expectancy. GDP also affects life expectancy based on the country's development, and the HIV/AIDS death rate for children significantly impacts the robust regression model. And from there, years in school is also a crucial predictor, explaining 70.1% of the variance, and education also correlates with awareness of health decisions made on impact of life expectancy. Thank you for watching our presentation, and we hope you were informed after this presentation.